Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. Formation evaluation, in its broadest sense, ranges from the macro scale of a geologic basin mapped from satellite imagery to the micro scale of a pore throat examined through a scanning electron microscope. Whether at these extreme scales or somewhere in between, as in this well bore, the principal objectives of formation evaluation are to determine the size, the shape, and the lithology of a reservoir, and to characterize reservoir properties such as porosity, permeability, and fluid composition.
Welcome to our series on wireline logging. In this introductory module, GL401, we'll concentrate on fundamental downhole logging techniques and practices and see how they apply to formation evaluation. In Unit 1, we'll look at field equipment and general practices used during a well logging survey.
In Unit 2, we'll look at what logs can tell us about rocks, fluids, and conditions near the borehole.
But first, let's place wireline logging in perspective with other formation evaluation techniques.
As discussed in your manual, wireline logging is the common meeting ground for many diverse formation evaluation techniques. For example, geologists use wireline data, such as dip meter logs, to confirm or refine structural interpretations made from broad area imagery and outcrop studies. Geophysicists use downhole acoustic logging techniques to determine velocity profiles in an area in order to calibrate and accurately interpret seismic surveys. And engineers use a variety of logging techniques to design completion programs and estimate the composition and recoverability of reservoir fluids.
During the remainder of this module, we will emphasize open hole logging. For discussions of wireline devices used primarily in cased hole and production logging, you should rely on your manual. But keep in mind that wireline logging techniques can be used throughout the life of a well, from the time the well is drilled through its entire testing and production cycle, even to determine its depletion and point of abandonment. Let's begin Unit 1. We'll begin learning about wireline logging by going into the field and observing logging equipment and practices that are commonly used in open hole formation evaluation. Logging operations are conducted using wireline logging units. Two general types of logging units are in common use.
One is a skid-mounted immobile unit permanently attached to an offshore platform or used at a remote land location. Its primary function is to service that particular drill site. The other type is a truck-mounted mobile unit, which is generally assigned to a field dispatch office. Its primary function is to service the local onshore area. There are 6 basic components common to both offshore and onshore logging units. These components are a suite of logging tools, a multi-conductor logging cable, a winch mechanism, a winch control panel, computer recording and processing equipment, and support capabilities. A suite of commonly used downhole logging tools is present at the unit. In addition, special purpose tools such as sidewall coring guns and formation fluid testers may be on hand. A multi-conductor logging cable serves to physically and electrically connect the logging tools with a logging unit. The cable attachment mechanism, shown here, or head as it is called, is also designed to be the downhole weak link or break point of the cable system. Should the tool string become stuck in the hole, This weak link is designed to break before the cable snaps, avoiding costly fishing jobs for wireline. The winch mechanism is used to lower and raise the cable and attached logging or sampling tools into the wellbore. A winch control panel measures the amount of tension on the cable and operates the winch at optimum speeds for various logging tools. Also, the tools can be positioned at precise depths for necessary tests and measurements. The computer is vital for receiving, viewing, and adjusting downhole tool responses, for storing and manipulating data, and for recording field logs. And finally, support capabilities, such as a generator to supply electrical power to the unit, a darkroom to develop log film, and reproduction facilities for making field copies of logs are considered standard equipment. In some units, satellite communication equipment is available that transmits log data directly to oil company offices, or, if required, to regional processing centers for further interpretation.
An open-hole logging survey can be thought of as consisting of 3 phases. The first phase includes mobilization of the logging unit, on-site rigging up, and field calibration of logging devices. The second phase is the logging phase, during which tools are run and the system is adjusted to hole conditions and previous logging runs. Logging measurements are taken during this time. The third and final phase concludes the survey and comprises on-site after-logging calibration and rigging down. The preparation of the field prints and well site interpretations must also be completed. Remember, as we discussed these phases in Unit 1, each phase can carry its own set of costs for the well operator. And, as with all drilling services, these can vary with supply and demand of equipment and the general economic climate of the industry. To get a feel for on-site logging operations, we'll travel along with a typical onshore truck-mounted unit while its crew conducts an open-hole logging survey.
Usually, the oil company representative calls a week or so before a logging unit will be needed to place the service company on call. At this time, all pertinent information regarding the well and type of surveys needed is given. Essential information includes hole diameter, total depth to be logged, and peculiarities of downhole conditions, such as the type of drilling mud or a deviated hole. Knowledge of these on-site factors is often critical in determining if special equipment will be needed at the well site. At this time, the oil company representative and the service company will often agree upon the amount of lead time required to notify the service company prior to logging. In remote and offshore areas, the logging crew may already be on site, depending on the type of service contract negotiated with the oil company representative. The objective of the notification is to provide adequate mobilization and setup time for the logging crew, and to minimize idle time either for the service company or the rig crew. At the time of notification, the oil company representative should again review the tools that are scheduled for the logging survey and update any well site conditions that may affect the survey. When notified by the dispatcher, the logging engineer and crew prepare the unit at the field office for the specific logging survey. The unit will bring the tools required for the necessary runs. These tools will have already been shop tested and calibrated to standard responses during a master calibration. These calibrations are performed periodically according to service company requirements. For example, the induction tool shown here was shop calibrated by several tests. Based on tool measurements obtained from these tests, the uncalibrated induction responses of this specific tool were then mathematically adjusted to produce standard readings. All test results and calibrations are included in the shop summary shown here and are made part of the permanent record of the induction tool.
You'll learn more about industry standards and how each type of logging device is calibrated in GL 402, well logging tools and techniques.
As loading of the logging unit continues, radioactive sources for nuclear logging tools are transferred from their secure storage area to a secure carrying compartment in the truck. If sidewall coring is a possibility during the logging program, These explosive-bearing tools are also taken from their storage area and placed in the unit.
When the logging unit is fully loaded and the well site and time of departure are confirmed with the dispatcher, the logging unit will leave for location.
It is the logging crew's responsibility to find the drill site and be at the location at the specified time. Under certain conditions, special equipment may be situated at the well site to ensure that the logging unit can be brought onto the lease. The preferred location for setup and logging is for the logging unit to be in a backed position, beyond the pipe rack, and accessible to the end of the catwalk, with an unobstructed view of the rig floor. This location provides the logging crew with a workspace needed to lay out, assemble, and test the logging tools. It places the logging truck and winch operator in favorable alignment with the derrick floor and allows the visibility of all personnel throughout logging operations. As shown here, rigging up includes laying out the logging tools, testing the cable head and cable, testing the logging tools, checking out the surface equipment, and making routine checks of mud properties. As logging devices are assembled together and the string of tools is made fully operational, a before-survey calibration check is made. This confirms that any changes in tool responses from the shop calibrations are within allowable limits or can be explained. For example, nuclear devices like this neutron density tool are tested with and without the calibration jigs designed to produce a predetermined tool response. Still other devices use built-in calibration tests, like the internal resistors in this resistivity tool. All before-survey calibration check data are added to the permanent records of each individual logging device and are included in the final printout of the logging survey. Once the drill pipe is clear of the rotary table, the next step is to rig up. This procedure includes hanging the sheave wheels, threading the cable through under the bottom wheel and over the top wheel, then attaching the cable head to the uppermost tool and raising the tool string. A cable tension gauge is always used and may be attached to either the upper or lower sheave wheel.
It is important to remember that these sheave wheels will be points of maximum stress during the logging run. Care should always be taken to see that they are well secured. Final steps in rigging up can now begin.
The tool string is raised in the derrick and suspended over the hole. At this point, the well's depth reference, or 0 point, is set into the cable depth measurement systems. As noted in log headings, this reference point is usually the Kelly bushing, but may be the derrick floor or any point selected by the oil company representative.
You'll learn more about this and other log heading information in GL 402. If the survey includes a radioactive device, the last step in preparing to log is now taken.
The rig floor is cleared of any non-essential personnel, and the radioactive sources are placed in the tool. The hole should be covered during this procedure to ensure that the sources do not fall into the hole. After the sources are inserted, the tools are lowered into the hole.
With all logging devices now tested and operational, the logging phase can begin. At this point, we need a word about depth determination. This process involves more than simply lowering the tools to total depth and reading the depth on the meter. Service companies use certain procedures to ensure that the depth reading is as accurate as possible. Check with your service company for an explanation of their particular procedures.
Now, as the string of the logging tools is lowered into the hole, the logging engineer again tests tool responses. Often, benchmark lithologies like salt or anhydrite are used to confirm that accurate readings are being obtained. Once the tool is on bottom, the logging run can begin. Usually, logging is done in the uphole direction. This procedure is used in order to maintain a constant logging speed and good depth control, and in some cases is required by tool design. Sometimes, in problem holes, logging going down the hole may ensure that some data is obtained in case problems are encountered. The speed at which logging is carried out depends on the logging tools in the string. Each tool has a maximum speed at which it can be run. In general, the slower the tool is run, the better, although, of course, practical aspects such as the cost of rig time must be taken into account. The whole condition, tool design, lithology type, and concern for quality data should be the predominant factors in determining what the logging speed should be.
If you are not familiar with the various logging tools at this point, don't worry. You'll learn more about them in GL 402. Now, let's look at the logging run in more detail. Nowadays, for convenience, the repeat section is logged first, close to TD, which is usually near the zone of interest. Logging this repeat section is essential for documenting that the logging tools are operating normally and producing repeatable results. Repeats are usually run over the zones of interest so that a quick log is available for analysis. Sometimes it's advisable to run short repeat sections over anomalous intervals to ensure that the tools are operating properly. It is during the repeat survey that the logging engineer generally confirms that measurements being taken by the different logging devices in the tool string are plotting on depth. As you can see by looking at this tool string, numerous detector points are located throughout its length. No two devices are logging the same depth at one time.
In order to adjust this sequencing of detection so that all measurements for one depth plot together, data from all upper sensors are stored and fed back into the log plot when the lowermost sensor crosses the point being measured. This log plot is displayed in real time on a monitor within the logging unit. For the on-depth check, the logging engineer verifies that proper displacement to one common depth point is valid. This is done by comparing all curves at lithology breaks to determine that they show lithology changes at the same depth. If not, the logging engineer makes any necessary adjustments so that on-depth plotting occurs. After logging the repeat section, the tool is lowered to bottom, and the repeat section log is examined. Now a final depth check is made, and with the repeat section in hand, the logging engineer gives the go-ahead for the main survey to begin. Throughout the period of uphole logging, the oil company representative may sit with a logging engineer and evaluate initial logging results. The curves are compared to reference logs from nearby wells to make stratigraphic correlations. And important initial evaluations of zones of interest may be made at this time. As the string of tools moves uphole and passes through possible prospective intervals, the oil company representative studies the evolving curves with the logging engineer, and, if necessary, asks for a rerun over critical intervals. As logging proceeds, a permanent record of digital data is made on tape, and a visual record of tool responses is made on film. At the end of the run, the film is prepared on board the unit, and further on-site evaluations can be performed. Digital data are often evaluated and integrated at the well site through quick-look computer programs on board the logging unit. When logging of the selected interval is complete and the logging string is brought to surface, essential steps still remain before the logging phase is considered complete. The logging engineer must check to determine that the logging tools functioned normally and responded accurately to downhole conditions throughout the run. A quality control scan of the logs is usually done to verify this. Additionally, the logging crew must complete the after-survey calibration check. This involves repeating many of the same calibration checks that were carried out before the logging tools entered the hole, and entering these after-survey results in the tool check summary of the final printout of the logging survey. Such after-logging calibration checks are needed to confirm that tools responded consistently throughout the run.
When both the oil company representative and the logging engineer agree that the logs are good and any anomalous measurements are satisfactorily explained, the run is considered complete. If the logging survey consists of a single logging run, downhole logging is now complete and rigging down can begin. Sometimes several logging runs using different tools or sampling devices will be carried out during the survey. In the procedure of before survey calibrations, proper depth recording, repeat, logging, and after-survey calibrations are similarly carried out.
It is important to note that sometimes subsequent logging runs can be based on the results of the first run, as in the sidewall coring run being set up here. Therefore, it is essential that the oil company representative and the logging engineer communicate effectively with each other throughout the survey, and that accuracy and details are obtained on the initial field prints. It is possible to transmit logging data via satellite or facsimile machine directly to the oil company's offices. This can be done after the logging run is complete and permits staff geologists and engineers in their offices to approve a run, participate in the selection of sidewall coring and fluid sampling depths, and modify subsequent runs of a logging survey. Upon completion of the last logging or sampling run, rigging down proceeds in a manner similar to the reverse of rigging up. Any radioactive sources are removed from their devices. Logging tools are lowered back onto the catwalk, cleaned up, broken down, and racked for transportation back to the field office. Shiv wheels and accessory items are detached and stored in the truck, and the cable system is secured. Field prints are made for the oil company representative. The logging survey doesn't end when the logging unit leaves the well site. Activity may move to a log evaluation center, where final prints, and in many cases, second-generation logs, additional downhole evaluations, and graphic summaries are made by the logging company in its log evaluation facilities. If requested, final results from these evaluations can often be transmitted to the oil company office in less than 24 hours. Routine processing, however, can take from 2 to several days.
This brings us to the end of Unit 1. Please take some time to study the corresponding sections in the manual and work the appropriate exercises. That will prepare you to move into Unit 2 and our discussion of the downhole logging environment. We've introduced the basics of well logging. Now, in Unit 2, let's examine formation properties, resistivity, and density measurements, and the downhole environment. As mentioned earlier in the introduction to this module, a major objective in formation evaluation is to recognize lithologic units penetrated by the borehole and to understand their reservoir properties. Let's look at a section of the borehole represented by this core to understand the parameters of interest.
There are 3 physical properties of this core that determine whether the reservoir it represents will or will not be commercial. These properties are the rock's porosity. Is there enough void space in the rock to hold an adequate volume of hydrocarbons? The rock's permeability. Can the hydrocarbons in the pores be produced at economical rates? And the rock's fluid content, or saturation. Is the recoverable fluid going to be largely hydrocarbons or mostly water?
We'll look individually at porosity, permeability, and water saturation to see how they are measured, and then evaluate how their mutual association affects reservoir characteristics.
Porosity, as indicated here by the symbol phi, is signified by a percentage and represents the volume of pore space divided by the total volume of the rock. Therefore, a rock with 12% porosity has 12% of its volume made up of void spaces. These pore spaces can be any size or shape. They can be relatively isolated or highly interconnected. Pore space in a rock depends on many factors. For example, porosity is dependent on how detrital grains in a rock are stacked together. As shown here in this generalized cubic stacking of spheres, grain stacking can be rather open, resulting in high porosity. Or stacking can be closer, as in this orthorhombic pattern, this tetragonal arrangement, or this rhombohedral pattern, and result in lower porosities. Although nothing has changed except the 3-dimensional stacking of spherical grains, porosity has decreased from about 47% in the cubic pattern to about 25% in the rhombohedral arrangement. Of course, these figures assume that the spherical grains are solid. If they have intragranular porosity, as shown here, the total porosity would be greater and represent the combined intergranular and intragranular porosity. Other factors that alter porosity include variations in grain shape and the degree of sorting. In the case of sorting, the poorer the sorting, the lower the porosity, since smaller grains may fill in the pore spaces between larger grains. Porosity may be greatly affected by such secondary features as cementation, which can decrease primary porosity in a detrital rock, or by features that increase porosity, such as dissolution or fracturing. Permeability defines the ability of a reservoir to permit the flow of fluids. It is measured in Darcy's or millidarcies and is represented by the letter kappa. A permeability value can be indicated, but not directly measured from well-logged data. Core analysis, however, can provide an actual measurement.
How is a permeability value calculated? Let's consider a uniform porous medium that is completely saturated with a single homogeneous fluid. According to Darcy's law, the volume of fluid flow per unit of time, Q, is equal to the negative of the permeability multiplied by the cross-sectional area multiplied by the pressure gradient and divided by the viscosity of the fluid and the length of the rock sample.
Therefore, the permeability is 1 Darcy when 1 cubic centimeter of fluid flows in 1 second through a medium that is 1 square centimeter in cross-sectional area and 1 centimeter in length, under a pressure differential of 1 atmosphere per centimeter, where the fluid has a viscosity of 1 centipoise. Permeability is controlled by the size of the pore throats, the connecting passages between pores. Permeability often decreases with depth because compaction and cementation restricts or blocks fluid pathways, and therefore reduces flow rate. We will be discussing 3 types of permeability in this video: absolute, effective, and relative. When only one fluid, such as water, exists in the pores, its permeability is known as absolute permeability, K. When 2 fluids are present, such as oil and water, the permeability of the oil is known as its effective permeability, K sub O. The effective diameter of the pores through which the oil is flowing is reduced by the water, which adheres to the grains. Therefore, effective permeability is less than absolute permeability. And finally, relative permeability, K sub RO, is the ratio of the effective permeability of a given fluid to its absolute permeability. Standard curves plot the relative permeabilities of the 2 fluids as a function of water saturation. Thus, in a typical relative permeability curve, we see that at low water saturation, only oil will flow. As the water saturation increases, the relative permeability of the oil decreases until some critical level is reached, at which both oil and water flow. The oil flow continues to decrease and the water flow to increase as water saturation increases. At some level of water saturation, oil no longer flows and only water flows. Beyond this point, as water saturation increases, the flow of water within the rock continues to increase.
However, the amount of fluid flowing is not a direct effect of the relative permeability, as different fluids have different viscosities. For example, if gas and oil have equal relative permeabilities, more gas and oil will flow within the rock because of the difference in viscosity. For a more detailed discussion of these types of permeabilities, see the engineering module PE 405, Core Analysis.
Porosity and permeability aren't always directly related. A rock with high vulgular porosity can have low permeability because the pores are not well interconnected. Conversely, this dense rock of relatively low porosity and storage capacity can have a high effective permeability and transmit fluids rapidly because of interconnected fracture planes.
However, in general, the association between permeability and porosity can be approximated as long as we restrict our conclusions to comparable rock types. Qualitatively speaking, when porosity increases, so does permeability.
This chart shows the general relationship between porosity and permeability for many types of reservoirs, such as riephal limestone, oolitic limestone, sucrosic dolomite, intercrystalline limestone and dolomite, well-cemented sandstone, chalky limestone, and fine-grained friable sandstone. But to restate our initial point that permeability and porosity are not directly related, if we look at a permeability of 10 millidarcies on the plot, we can see that porosities range from less than 10% to over 30%, depending upon rock type. Therefore, when taken alone, a porosity or permeability measurement won't necessarily provide an accurate approximation of the other. The amount of a given fluid in a rock is known as its fluid saturation. Since pore spaces are considered to be entirely filled with fluid, the total fluid saturation is always equal to 1, or 100%. In a three-phase system, the composition of reservoir fluids consists of a percentage of water, plus a percentage of oil, plus a percentage of gas. Fluid saturation is represented by the symbol S and expressed as a percentage. Therefore, total fluid composition is S sub W plus S sub O plus S sub G equals 1. The notation that S sub W equals 0.45, as shown here, means that the water saturation is 45%. Consequently, hydrocarbons make up the remainder, or 55%, of the pore space fluids. During log analysis, you might see such expressions rearranged to show hydrocarbon content as hydrocarbon saturation, S sub Hc, equals 1 minus water saturation, S sub W. This reservoir shows an oil-water contact. In a formation where the clay content is negligible, we might expect to see a low water saturation within the oil portion of a reservoir, while below the oil-water contact, water saturation would approach 100%.
It is essential to note, however, that the water saturation percentage determined at any point in a reservoir will not necessarily be the percentage of water recovered with hydrocarbon production. This is a critical factor in wireline log and reservoir evaluation. Let's look into it further. Many petroleum reservoirs are water wet. Initially, reservoir pore spaces were filled with water, and later, hydrocarbons migrated into the reservoir to displace the water. The result is water-wet surfaces, but primarily hydrocarbon-filled voids. As we discuss more completely in the manual, this subsurface condition causes both water and hydrocarbons to be present in different proportions and with different recoverabilities.
The first factor that causes oil and water to mix takes effect when hydrocarbons migrate into a reservoir. The formation water is displaced, and the surface tension of water across the pore throats is too great for capillary forces to force the water out. This means that in water-wet reservoirs, there will always be a certain amount of formation water trapped and retained along rock surfaces. The saturation of this trapped water is known as the irreducible water saturation, S sub Wi. Irreducible water will plot like this on a water saturation curve in the reservoir where oil is a continuous phase. This water will not move when the reservoir is produced, and, therefore, will not show up in the produced fluid. The general association is, the lower the porosity of the rock, the greater will be the saturation percentage for irreducible water. The second factor that causes oil and water to be mixed in a reservoir is capillary action at the oil-water interface. Capillary forces within the pore spaces cause the formation water to move up into the oil column. Once equilibrium has been reached, a transition zone has been established. In laboratory tests, the smaller the capillary tube, the more effective the capillary action and the upward movement of water. Therefore, we would expect the transition zone generally to be thick in reservoirs with small pore throats, and thin where pore interconnections are large. The percentage of water that will be recovered from the transition zone depends upon the relative permeability of the reservoir rock to the combination of water and hydrocarbons that is present. Near the top of the transition zone in a water-wet reservoir, hydrocarbons will make up a higher percentage of the produced fluid. For example, as water saturation increases in a water-wet rock, it is easier for the water to move than it is for the hydrocarbons. As water saturation reaches 75%, the relative permeability to oil nears zero, and no hydrocarbons will be recovered. The remaining hydrocarbons are referred to as the residual hydrocarbon saturation, S sub OR. As stated earlier in our definition of relative permeability, when residual hydrocarbon saturation is reached and 100% water is produced, the relative permeability of the system to water is not 100% of the absolute permeability. In this case, relative permeability is 40% of absolute permeability. You can also note that in an oil-wet system, oil-water relative permeability follows the same pattern as that for a water-wet system. However, it starts with a lower irreducible water saturation and has a greater relative permeability to water as residual oil saturation is approached.
With this background information, it is time to discuss how logging tools can obtain the necessary information so that we can properly evaluate formations. Now, no single logging tool can precisely identify the lithology of a formation or directly measure its porosity, permeability, and fluid saturation. However, by combining measurements from different logging tools, it is possible to solve for these critical variables. For example, two important measurements that can be made by logging tools are electrical resistivity and apparent rock density.
Formation resistivity, R sub T, is important because it is inversely related to water saturation. For example, in the uninvaded zone, all other things remaining equal, as the electrical resistivity of the formation decreases, the water saturation increases. Consequently, from changes in resistivity measurements, we can determine changes in water saturation, and therefore changes in hydrocarbon saturation. Density, indicated by the Greek letter rho, is important because it is inversely related to the porosity of a formation. In a given formation, as bulk density decreases, generally porosity increases. Therefore, if we measure the bulk density of a formation, we can estimate the porosity of that formation.
If you keep in mind the concept that formation evaluation generally solves for variables by combining a number of logging measurements, it should be apparent why we place a number of logging devices together or run them sequentially, and why we make interpretations from well logs that display measurements from more than one logging device. Now let's examine the borehole and the downhole environment in which logging tools operate.
As drilling proceeds and the borehole is extended into the earth, the drilling process alters the conditions surrounding the borehole. These conditions, in turn, will affect logging tool response.
In some cases, the effects of drilling can indicate formation properties. For example, if drilling mud filtrate penetrates a formation easily, a logging tool sensing this effect could be qualitatively indicating good permeability. In other cases, the effects of drilling with regard to log evaluation can be detrimental. For example, when the drilling process has created an irregular borehole, or the filtrate has penetrated deep into the formation, some logging measurements can be erratic, insensitive, or difficult to interpret. To characterize downhole conditions for logging purposes, the borehole and surrounding formation are generally envisioned to consist of 4 concentric zones. The first zone is the borehole with its mud and mud cake. The second is the invaded or flushed zone, where the mud filtrate has combined with mobile formation fluids. The next is the transition zone, where only partial invasion and flushing of formation fluids has occurred. And the fourth is the undisturbed or virgin zone, with its unaffected pore fluids. Of course, it is the analysis of the natural formation fluids in this outer, undisturbed zone, which more closely resembles the potential reservoir, that determines the presence of hydrocarbons. However, should hydrocarbons be present, the changes induced by drilling fluids in the altered zones are what indicate whether hydrocarbons are qualitatively movable.
Tools that measure the fluid content of the formation and record resistivity and conductivity have different depths of investigation. Therefore, it's possible to evaluate different zones separately using the Archie equation.
Applications of the Archie equation will be discussed in detail in the next module on well logging, GL402. But for now, let's introduce the symbols for various properties of the four zones.
For example, the diameter of the hole is designated D sub H. The diameter of the invaded or flushed zone is D sub I. And the diameter of the transition zone is D sub J. Thicknesses also receive symbols, such as the mud cake, H sub MC, and the bed being logged, H. If we use the same downhole setting and look only at fluid saturation, we'll see that another set of symbols is needed. S sub XO represents the water saturation of the invaded zone, and S sub W is the symbol of water saturation in the uninvaded zone. If we look at the electrical resistivity properties of some of these same fluids in different zones, other sets of symbols come into use. The symbol R sub M represents the resistivity of the drilling mud. R sub MF, the resistivity of the filtrate. And R sub W, the resistivity of the formation water. Additional symbols are used for the resistivity of the mud cake, R sub MC, the invaded zone, R sub XO, and the resistivity of the undisturbed formation is represented by R sub T.
The variety of symbols you have just seen should give you a fair idea of the types of variables encountered in wireline logging and formation evaluation. You'll deal with these variables many times over when you apply the Archie equation to the various zones in GL402.
In that module, we'll go on to examine the logging tools themselves. Specifically, we'll look at those tools that measure either a formation's electrical properties, acoustical properties, or nuclear properties.
In GL403, we'll see how data from various logging tools are combined to produce logs that evaluate specific formation and fluid properties. The final module in the series, GL405, will be devoted exclusively to dip meter interpretation.
What have we covered in this introductory module? We followed a logging unit out to a well site and observed the mechanics of logging a well. We've examined three physical properties of a formation that well logs indirectly measure: porosity, permeability, and fluid saturation. We've introduced two important measurements that can be made by logging tools: electrical resistivity and apparent rock density. And we've looked briefly at the borehole environment in which tools operate. Take time now to read your manual and study these topics. See you in the next module, GL402, where we'll look at specific logging tools.
This program has been sponsored in part by the following companies: Agit, Aramco, Chevron Corporation, Mobil Oil Corporation, OxyCity Service Oil and Gas Corporation, Petro-Canada Incorporated, Phillips Petroleum Company, Schlumberger Limited, the Shell Companies, Texaco Incorporated.